All right, hello everyone. We're going to go ahead. We're going to do our exam one review. So we're going to review a few important problems that are going to be on the exam, so we can get a good look at them and just review everything from chapter 2 and then also chapter 1 and 10, those two sections that we did as well. So starting off with our exam one review, we're going to go over 7 problems, hopefully. So here is our first example. So example 1, we want to show the equation represents a circle by rewriting it in standard form, then find the center and the radius of the circle. We have x squared plus y squared plus 6y plus 5 is equal to 0. So we're going to go ahead and we're going to go to our notes to work on this problem, not example 2. All right, so here we have our equation of our circle, x squared plus y squared plus 6y plus 5 is equal to 0. And we want to remember what the standard form of the equation of the circle is. It looks like x minus h squared plus y minus k squared is equal to r squared. And this is where we have that the center is located at h comma k, and the radius is r. So we see that in our standard form, we have x minus h squared plus y minus k squared is equal to r squared. So the radius is just r, so it's going to be the square root of whatever value we have there at the end. And our center is found at h and k. Now we've done this problem before back in section 1.9. We did a very similar problem to this. And when we did this problem, we had to complete the square. And we had to complete the square twice. We had to do it with x and we had to do it with y. We're going to see it's going to be a little different this time around, but just to remember, completing the square takes us from something that looks like x squared plus bx, and x is just an example, it can be y as well. So we have something that looks like x squared plus bx. We could add a strategic constant, that constant being b over 2 squared, which then factors into x plus b over 2, that whole term squared. So we use completing the square. We use completing the square in order to do this, because we see that this is going to be the result that we get when we try to simplify the problem that we have in example 1. And we're going to need to use completing the square in order to get our equation into standard form. So let's go ahead and work this out. So our first step whenever we have the equation of a circle and it's not in standard form is that we want to try to make it look as much as possible like standard form, which means that we're going to group our x terms and our y terms together with parentheses, and then we will send any value or constant that doesn't have an x or a y on it, and we're going to send it to the other side. So that means that we are going to group together the y squared and the 6y, and we're going to subtract 5 from both sides to get rid of that 5 on the left-hand side. I'm excellent with lefts and rights. All right, so on our left-hand side, we don't want any constant numbers. We only want x and y terms. So we're going to group x and y terms together on the left-hand side LHS and subtract 5 from both sides to move our constant value to the right-hand side, RHS. All right, so that's what we're going to do first. So if we notice, we really only have one x term. We only have x squared. And since it's by itself, we're just going to leave it by itself. So it's x squared. plus, and now we're going to group them. When we group them, this means we're going to put them side by side and we're going to put parentheses around each other. So we're going to put parentheses around the y squared plus 6y. And then we subtracted 5 from both sides to get that value on the right-hand side. So if we look at what we have right now, we have x terms by themselves, y terms by themselves, and then we have some number on the right-hand side, which is vaguely what looks like standard form. It's not exact, but it looks more similar to standard form than how we started. And once we get to this step, this is where we need to use completing the square. Since we said completing the square looks something like x squared plus bx, really the only thing that fits in this is going to be our y terms, because we have y squared plus 6y. Ooh. Oh, I used the eraser. Oops. There we go. All right, so y squared plus 6y is what we need to actually use completing the square on, because x is just x squared, it's just by itself. So first thing we need to do is identify what the value of b is in the y squared plus 6y. And if we look at completing the square, we know b is going to be the number right in front of the single y term. So we have plus 6y, which means that b would have to be 6. So now that we've identified that part, we're going to go ahead and we now get to add our constant b over 2 squared. So we still just have x squared. And we've got y squared plus 6y. And now we're going to have plus 6 over 2 squared. So we added that constant. Remember, anything we do to one side, we have to do to the other side. So if we added 6 over 2 squared to one side, we now have to add 6 over 2 squared to the other. All right. So we added our strategic constant, and if we look at completing the square, once you've added your strategic constant and, potentially added it elsewhere like we had to do, it now is immediately going to factor into x plus b over 2 squared. We don't have to actually do any work with this. Once we know what the value of b is, we can go ahead and plug it into its factored form without really doing any work. So since we know what b is 6, this means that our y squared plus 6y plus 6 over 2 squared, that whole term, immediately turns into y plus 6 over 2 squared. So we see that once we add that strategic constant, we can immediately put it in its factored form. They are now equivalent, and we don't really have to do any extra work to get there. Then we just have to simplify the -5 plus 6 over 2 squared. So we want to figure out, what is 6 over 2? 6 divided by 2 is going to be 3. So really we're looking at -5 plus 3 squared. And that value, if you guessed it, was 9. So we have -5 plus 9. Now we just want to do our final simplifications. So we have x squared, and x squared is just by itself. Now, in standard form, we really want, x minus h squared. We want x minus some number. And the only number that we can put in the place of h that wouldn't change x squared would have to be 0, because x minus 0 is just 0, and then x squared is x squared. So we have to replace x squared with an x minus 0 squared if we want to be able to use the center with that h and k and everything like that. Basically what we're saying is that if you ever go this far and you still have that one single term, that x squared or just y squared and nothing else, it really just means x minus 0 squared. So that's the only other thing that you can replace it with. It is essentially the same. It's just you have it in a form that you can now pick out, the h or k value of your center. So x squared is the same thing as x minus 0 squared. So now we have it in the standard form. Then we simplify y plus 6 over 2. 6 over 2 simplifies to 3. And then we have negative 5 plus 9. We add those two values together to get 4. So here's our equation in standard form. X minus 0 squared plus y plus 3 squared is equal to 4. We can go ahead and highlight that. That is our answer for standard form. Now, the second part of our question was that we want to find the center and the radius. And we said our center was found at h, comma, k. We say this is h, this is k, and this term right here, this is technically r squared. And our center is h, comma, k. So looking at our problem here, we see that h is going to be 0, because that is the value there. We have x minus 0, so h is 0. And then k, typically we want this to be subtraction. We want it to say y minus a number. In this case, we have y plus a number, which essentially means that we had y minus a negative number. It's the only way it would have been plus. So if you see a plus sign instead of a minus sign, just means that value is negative. So we say k is negative 3 instead of being positive 3, because it's a plus sign instead of a minus sign. Then our last part, our radius, we said that radius is r, not r squared. And in our standard form, we have r squared. So the radius is going to be the square root of the number you see there at the end. So our number at the end was 4. We take the square root of 4. And the value is 2. Now, typically when you take a square root of a number, you technically get that positive negative value at the end. We would say positive or negative 2. But your radius always has to be positive. So we wouldn't have negative 2 as a radius. We'd have positive 2 instead. And that would wrap up the end of our problem. So this was taking the equation of a circle and putting it in standard form, finding its center, its radius, and doing all of this completing the square, and in this case only once. So in section 1.9 we did the same problem or a very similar problem. The only thing that was really different was that we had to use completing the square twice instead of just once. So it could be worthwhile to go look back at that problem as well, just to get, the other type of problem that you could possibly see, on an exam, and kind of get that different type of problem there to get a wide range of the types of problems that you can see. Also, as we see here, the radius works out pretty well. Square root of 4 is 2. That may not always be the case. You could have, something is equal to 13, the radius would be the square root of 13. You could find that decimal value, or you could just leave it as the square root of 13. And either way, that would be totally okay. So just a few notes about problems like these. So let's go ahead. Since we finished up example 1, we'll go on to example 2. All right, so moving on with example 2, we want to evaluate a piecewise function. So we want to evaluate the following piecewise function at f of negative 5, f of negative 2, f of 2, f of 3, and f of 6. So we're finding 5 different values based on our piecewise function. Our piecewise function is defined as f of x is equal to 6x if x is less than negative 2. F of x is equal to x plus 2 if x is between the values negative 2 and 3, including negative 2 and 3. And lastly, f of x is equal to x minus 3 squared if x is greater than 3. So we see that we will use the different parts of our function, the different pieces of the function, depending on what the x value is. If the x value lies less than negative 2, if it lies between negative 2 and 3, or if it lies greater than 3. And you'll use those different functions based on the value of x. And we're given 5 different values of x in this case: negative 5, negative 2, 2, 3, and 6. So we're going to go ahead, we're going to evaluate each one of these values here in our notes. All right, so in our notes here, we have the problem written down again. We are just evaluating these 5 different values. So starting with f of -5. With f of -5, we're essentially saying here that we want to know what is our function when x is -5. So we're saying right here, x is -5. And if we want to know our function when x is -5, we need to find the correct function that corresponds to the correct domain. So we see that we have first x being less than -2, and then we have x being between -2, and that should be 3, not 2. There we go. Between -2 and 3, including -2 and 3, and when x is greater than 3. So if we're given a specific value of x, we say x is equal to -5, we want to figure out what function we're going to use based on the value of x being -5. So if we take -5 and we look at our 3 different functions on our 3 different domains, we can say that -5 is less than -2, which means that we're going to use the first function. So we can go ahead and try that out. So our first function is 6 times x. X is -5, so this function will be 6 times -5, which calculators or brains comes out to -30. So f of -5 is equal to -30. And then we have it. So we're just matching up basically on the given value of x. We're matching up our function with the correct function that we're using in our domain. So it's all based on this value of x. And then we plug it into that function and solve. So, all right, on our next one here, f of -2, we want to do the same thing. F of -2 essentially means that x is -2. And if we look to our function here, we have 6x if x is less than -2. Well, x is -2, -2 is not less than -2, it is equal. So our next function is x plus 2 if x is greater than or equal to -2 and less than or equal to 3. So our value of x equals -2 goes to the second function. It goes to the center function because this includes -2 and that's our x value. So we'll go ahead and use -2 in this function here. We have x plus -2. So this is really going to be -2 plus 2, which comes out to 0. So f of -2 would be 0. All right. So on to our next one, we have f of 2. We have established at this point that the number in those parentheses is x, so we have that x is 2 for this function, and if we look at our different domains here, we would say that 2 would lie in between -2 and 3. So we are once again using the center function. So we have f of 2, the function itself is 2 plus 2, and 2 plus 2 is 4. So we have f of 2 is equal to 4. All right, then our next one, f of 3. This means our function evaluated when x is equal to 3. And looking at our different domains here, we'd say that x is equal to 3. So this does still fall into our domain there of -2 less than or equal to x, which is less than or equal to 3. So we are once again using the middle function. So go ahead and use it. We're going to plug in 3 for x into x plus 2. So we'll get 3 plus 2, which is equal to 5. All right, then the last one here, we have f of 6. So we're saying now that x is equal to 6. So looking at our function, we know it's not our first domain with x being less than -2. 6 does not lie in between -2 and 3. 6 is greater than 3. So we get to use the last function now for this value. We're going to plug in 6 for x into our function. We're going to have 6 minus 3 squared. 6 minus 3 is 3. And 3 squared is equal to 9. And there we have it. We've evaluated all the different functions, all the different x values within our piecewise function. So just to send us off on this example, the last, or really the main part here for evaluating piecewise functions and just being able to tell what your x value is, what domain your x value would lie in, because you'll be given multiple, figuring out which one it is, and then the function that corresponds to the x value in that specific domain, and that is the function you'll use to evaluate your overall piecewise function. All right, that finishes up example 2. Let's go on to example 3. All right, so here we have example 3. We're going to find the domains of the function. So we have a f of x is equal to x to the power of 4 divided by x squared plus x minus 20. And part B, we have g of x is equal to the square root of 1 minus 3x. So we're going to go ahead, we're going to go to our notes, and we're going to find the domains of these functions. All right, so we have our two functions here for part A and part B, and we want to find their domain. Now, if we remember back from section, I believe it's 2.1, when we learned about domain, we learned about the two things that can really mess up domains. Because typically domains are just negative infinity to infinity, and it's two specific types of functions that would change that fact. And those two functions would be fractions that have an x in the denominator, so these are called rational functions. And what we have in part B here, g of x is equal to square root of 1 minus 3x, square roots, because you cannot take a square root of a negative number at this point in our class. So basically what we have here is that anything under a square root has to be greater than or equal to 0. And any function that has x in a denominator, so like a fraction with x in the denominator, your denominator just cannot equal 0 because you cannot divide by 0. So those are the two specific types. So obviously, those are the two types of problems that we see here in example 3. So we're going to go ahead, we're going to figure out how to solve these. So starting off, here we have our fraction, we have x in the denominator. Like we said before, we just don't want our denominator to equal 0. So our denominator can't equal 0. And we know what our denominator is. It's x squared plus x minus 20. We're saying that that can't be 0. So really the problem that we're dealing here with is this problem here. And even though that sign there is not equal to, we could solve this problem the exact same way as if it said equal to. So what we're going to do is we're going to factor x squared plus x minus 20 into its factored form, and then find the two values of x that can't exist. So starting with factoring x squared plus x minus 20, when it comes to factoring things like this, we're really looking for two values that would add to the middle number and multiply to the final number. So we would have x squared plus a plus b, x plus a times b, and then not equal to 0. But this is how we're going to factor this. Its factored form would look like x plus a times x plus b. So in our case, we have 1 being x, so we want two numbers that are going to add to 1 and two numbers that are going to multiply to negative 20. And then this will factor into those two numbers, x plus that number times x minus that number. So if we take a second to think about this, two numbers that are going to be adding to positive 1 and multiply to negative 20, those two values are going to be positive 5 and negative 4. So this will factor into x plus 5 times x minus 4. And our statement here still does not equal 0. So once we've factored, we can go ahead and separate these out, because if either one of these terms were equal to 0, the whole thing would equal 0. So we're going to separate them by factor. So we're going to have x plus 5 does not equal 0, and x minus 4 does not equal 0. Because both of these things can't equal 0, and they definitely both can't be 0. So we're going to go ahead and we're going to solve the two separate statements. If we want to know what x can't be equal to, but the x plus 5 can't be equal to 0, we're going to subtract 5 from both sides. This leaves us with x cannot be negative 5. Then on the other side, we're going to add 4 to both sides. And this will leave us with x cannot equal 4. So we have two numbers that our function is not defined for those values of x. So our function is not defined for values of negative 5 or 4, but any number other than that. So the best way to find our domain is to draw a number line. This gives us a little bit of a visual, and it's really going to help us figure out, the order of the intervals and how we're going to write them and everything. So you draw your number line, negative infinity to infinity, and you're going to fill in the two values where your function can't exist. So you've got negative 5 and 4. And at those values, your function doesn't exist, so you draw a big circle around those spots. And your function exists everywhere else. So I like to draw little squiggly lines everywhere else to indicate my function existing. Really anywhere else, once again. So now that we have our number line, we have this visual now of how our intervals should be written, because we always want to write our answers in interval notation. So this first interval, and you always go from left to right. So starting on the left, we have negative infinity up to negative 5. And we can't include 5, we have that big open circle, or we can't include negative 5, this is a big open circle, so we have parentheses. And we always put parentheses on infinities as well, so negative or positive infinity. So we have our first interval. We're going to write our second interval, and our second interval, and this was the first one, now we have the second, and this will be the third. Our second is all the values between negative 5 and 4. Since we still can't include negative 5 or 4, we're still using parentheses. And we're going to write out that interval, negative 5 to 4. Then our last interval is going to be 4 to infinity. Once again, still using parentheses. So we have our 3 intervals. These are the 3 intervals that are correct. Whenever you write interval notation and you have multiple intervals, you need to connect them with unions. So we're going to put these big U's in between those intervals there. And this part right here is our final answer for domain. This whole answer here is the answer for domain. So when the problem asks us, what is the domain of f of x? The domain is negative infinity to negative 5, union negative 5 to 4, union 4 to infinity. So that would be our answer for part A. So now moving on to part B, we have g of x is equal to the square root of 1 minus 3x. So previously in part A, we said that the denominator just can't be 0. But when it comes to square roots, nothing under the square root can be negative, meaning it can be 0 and it can be positive, but it cannot be negative. So we're going to say that whatever's underneath the square root, which for us in this case is 1 minus 3x, has to be greater than or equal to 0. So the statement that we're dealing with is 1 minus 3x has to be greater than or equal to 0. And now this is a pretty basic inequality. We're just going to solve for x. So we're going to subtract 1 from both sides. We'll get negative 3x is greater than or equal to negative 1. We want to get rid of the negative 3 in front of the x. So we'll divide each side by negative 3. When you divide by a negative number in an inequality, your sign has to change direction. So we had that x had to be greater than or equal to some number, but when we divided by that negative number, the sign has to change. It's something very important to remember in problems like these. So we divided by negative 3. We now have x is less than or equal to 1/3. If you want to avoid the whole situation, you could add 3x to both sides and then divide by a positive 3. So the sign doesn't have to change, but you will read it differently anyway, because you would say that 1/3 is greater than or equal to x, which inherently means x is less than or equal to 1/3. So just remember you can do it either one of those ways, but it is something to look out for whenever you're dealing with inequalities, looking out for that, am I dividing by a negative number? Should my sign be switching, yes or no? All right, so we have here that x has to be less than or equal to 1/3. So we know the statement, we now need to write our answer in interval notation. So just like before, we're going to go ahead, we're going to draw out a number line. And here is our value of 1/3. Now, we have that x is less than or equal to 1/3. So unlike our previous problem, we can include 1/3. So we're going to put a big colored in circle on 1/3. So we are including 1/3 in anything less. Since our number line goes from negative infinity to infinity, and we're saying that it's anything less than 1/3, we're going with all the numbers on the number line to the left, because these will be numbers like 0, which is less than 1/3, and negative 5, which is less than 1/3, and all the way down to negative infinity. So this is the side of our graph that follows the interval. Another way I like to remember it is that you have the sign, the sign kind of looks like an alligator or a carrot is what people say a lot of the time. So you have this alligator, the carrot. If you imagine it like an arrow, the arrow is pointing in a left direction, so it's pointing to the left. So that's the side of your number line that you would color in. So that's another way, an easier kind of way to remember it, if you choose to remember it that way. But all right, so this is the only part that we have to color in for our domain. We're just not including any numbers that are going to be greater than 1/3. So our number line starts at negative infinity because you're always going from left to right. So we start at negative infinity and we're going to go up to 1/3. And since we included 1/3, that point is filled in, it gets a bracket instead of a parentheses. And this is our answer for domain. So when given the problem, g of x is equal to the square root of 1 minus 3x, and you need to say what the domain is. The domain would be negative infinity to 1/3, including 1/3, so with the bracket, that is its domain written in interval notation. So, all right, that wraps up problem 3 with domains, the 2 types of things that can really mess up your domain. And there we had it. Those are the 2 types. Those are going to be the ones that you're going to see most often and potentially on the exam. All right, let's go ahead and move on to example 4. All right, so example 4, we have a pair of points are given, -8, -5, and 1, 7. So we have 2 points. Part A, we want to plot the points on a coordinate plane. Part B, we're going to find the distance between these 2 points. And part C, we're going to find the midpoint of these 2 points. So let's go ahead and go to our notes to work on the problem. All right, so here we are. We have problem 4. We are plotting the 2 points on a coordinate plane, and then we're finding their distance and midpoint. So looking at our points here, we have our coordinate plane that I drew in. we're going to draw the first point in red and the second in blue. So starting with the first one, we have -8, -5. We're going to find the value of -8 first on the x-axis and then go down to -5. So on the x-axis, we always have to start at the origin. We go to -8, and then we go down to where we believe -5 should be, which looks to be about, maybe not quite right there, maybe a little lower. Oop. My pen ran away. Yeah, probably about right there. If you would be given this problem on the test, it would be very clear. It would have, all of the lines and everything. It'd be very straightforward on plotting those points. So not quite as finding where they are, like how I drew here. But so this point, this is our -8 and -5. Then we want to play 1, 7 as well. So on our graph, we'll go to x equals 1, and then we'll go up to +7. Which should be about right here. So this is the point 1, 7. And that's all we need to do for part A. Part A just wants us to plot those 2 points. You wouldn't even need to necessarily label them with their -8, -5s, or 1, 7s. You would not necessarily need to label them. You just need to plot the 2 points. Then we go on part B. Part B was asking us to find the distance between the 2 points. And the distance formula we want to remember is that distance is equal to the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So this is our formula for distance. So we have the distance in x squared plus the distance in y squared with our square root underneath all of it. So we want to identify first off, which is x sub 1 and x sub 2, which is y sub 1, y sub 2. Let's go ahead and say that -8, -5 is our point 1. So this means that x sub 1 is -8 and y sub 1 is -5. Then we can say that 1, 7 is our point 2. This will be x sub 2 and y sub 2. So when we plug this into our equation for distance, we'll have x sub 2, which is 1, minus x sub 1, which is -8. And that whole term is squared. And I'll say, I think for the y's, we have y sub 2 is 7, minus y sub 1 is -5. And that is also squared. So we want to add these together, we want to simplify. We know that double negatives mean plus, so this is really 1 plus 8 and 7 plus 5. So 1 plus 8 is going to be 9, and 7 plus 5 is 12. So we have the square root of 9 squared, that's parentheses, 9 squared plus 12 squared. 9 squared is 81, and 12 squared is 144. Adding these together with, calculators, brains, comes out to the square root of 225. And if we take the square root of 225, this comes out to 15. So the distance is equal to 15 in this case. Now, if you happen to get a number that doesn't quite simplify as easily as the square root of 225, you would just either leave your answer as that square root value, or you could turn it into the decimal form. Either way, you would get full credit on the test for having either form. But, potentially if you did happen to mess up, kind of how to write one, writing both would probably ensure that you would get at least one of them right. Since they are the same, you can definitely write both if you would like. The same does not go for things like multiple choice problems and whatnot. But yeah, since like the decimal and the square root form are technically the same number, it would be okay if you did write both, if you wanted to write both of them. But you could also just leave it in the square root form or its decimal form. So if the number wasn't as nice, say the square root of 90, you could just leave it as the distance equals the square root of 90, or you could turn it into its decimal form, whatever that is, probably 9 point something at that point. So you could do either for finding the distance. Then part C, we want to find the midpoint that lies in between these 2 points here. So our midpoint formula is x sub 1 plus x sub 2 divided by 2, and y sub 1 plus y sub 2 divided by 2. And this will be in the form of an ordered pair. So we know what x sub 1 and x sub 2 and y sub 1 and y sub 2 are, so we're just going to fill in these values. X sub 1 we said was -8, so we're going to have -8 plus 1 divided by 2. And then we're going to have y sub 1, which is -5, plus y sub 2, which is 7, divided by 2. Now I want to simplify. -8 plus 1 is going to be -7, so we get -7 over 2. And -5 plus 2 is 2, divided by 2. Now, we know that 2 divided by 2 is really just 1. So our answer would be -7 over 2, comma 1. If you wanted to write the decimal form, you could do that as well. This would also be -3.5, comma 1. So either way, both of these answers are correct. You don't have to write both, just one of them. And you do not have to put the midpoint on the coordinate plane. Coordinate plane was just for part A, just for plotting those 2 points. It's not for drawing a line. It's not for drawing a triangle. It's not for drawing the midpoint. The whole point of part A is just, can you plot 2 points, and done. So don't draw anything else. Once you find your midpoint, you know what the midpoint is. That's great. You put it in, in its rightful spot, and you'll move up, and you'll move up. So, all right, that finishes up example 4. So let's go ahead and do example 5. All right, so for example 5 here, we want to find the net change and the average rate of change between the 2 given values of the variable in the given function. So our function is g of x is equal to 1 minus 5x, and we have the 2 values of x, -3 and 2. So we're going to go ahead, we're going to use our net change and our average rate of change formulas to find our net change and average rate of change for our function between these 2 x values. So let's go ahead and go on over to our notes to do this. All right, so here we have our formula. We have g of x is equal to 1 minus 5x, and then we have x equals -3 and x equals 2. So we're starting with the net change, and the formula for net change is f of b minus f of a when a is less than or equal to b. So a has to be less than b. So when choosing the values of a and b, we want to make sure that a is the lower value and b is the higher value. We have the values of x equals -3 and x equals 2, so a will be -3 and b will be 2. Then we want to find the function values of a and b. So we're going to start off with f of a. F of a would be f of -3. And so we're going to plug in -3 into our value of x. We're going to go ahead, we're going to change the color of this. There we go. So we have f of a is f of -3. So we're plugging in -3 into x in g of x. G of x is our function. That's why you write f instead of, say, g or anything else. So our function evaluated at -3 would be 1 minus 5 times -3. So I want to simplify. 5 times -3 would be -15. And then we have 1 minus -15. We have a double negative here. We know that this means plus. So really we have 1 plus 15, which comes out to 16. So f of a is equal to 16. Now we also want to find f of b. F of b is f of 2 in this case. So we're going to go ahead and we're going to plug in 2. So we're going to have 1 minus 5 times 2. 5 times 2 is 10. So we have 1 minus 10, and 1 minus 10 is equal to negative 9. So we now know the values of f of a and f of b, so we can go ahead and plug this into our formula for net change. So we said net change was equal to f of b minus f of a, which for us is going to be f of 2 minus f of negative 3. F of 2 we said was negative 9, and f of negative 3 was 16. So we have negative 9 minus 16, which simplifies to negative 25. So our net change is equal to negative 25. All right. Then for our formula for the average rate of change, the average rate of change is f of b minus f of a divided by b minus a. Now in the average rate of change, it doesn't necessarily matter what's a and what's b, but in problems like these, since you just did the net change, you may as well stick with what your values of f of a and f of b are. And on top of that, if we look at the average rate of change, the numerator is f of b minus f of a, which is the net change. So this is really the net change divided by b minus a. And we already know what the net change is. We said the net change was negative 25. So for us, our average rate of change, which is f of b minus f of a, divided by b minus a. We can plug these values back in if we would like, but we'll see the same thing will happen. We'll have net change divided by b minus a. So f of b we said was f of 2, f of a was f of negative 3, and we'll have 2 minus negative 3. This came out to negative 9 minus 16, 2 minus negative 3. It'll be the same thing like saying 2 plus 3. 2 plus 3 is 5. Then negative 9 minus 16 is negative 25, like we got for net change. So we could have skipped a few steps here if we would like. If not, you can definitely just do the steps again. So we have negative 25 divided by 5, which comes out to negative 5. So our average rate of change for this function was negative 5, which if we look, that was the number in front of x. So negative 5 would have been our average rate of change. All right, that wraps up example 5. Let's go ahead and do example 6. All right, so example 6, we want to find the compositions of f of x and g of x. So this would be f of g of x. So we see that circle operation there, meaning composition or composed. So f of g of x. And we also want to find g of x. So we're finding the composition of f and g, and then we're finding g composed with itself. And then we're going to state their domains. So f of x is 1 over x, and g of x is 10x minus 12. So let's go ahead and go to our notes to work on this problem. All right, so our first operation here, first composition, is going to be f of g of x, and we're going to find its domain. We know that f of x is 1 over x, and g of x is 10x minus 12. So f of g of x is the same thing as if we wrote it in this sense. So if we have it like this, and we know that f of x is 1 over x, we can replace x with literally just writing g of x. And then that'll help us kind of simplify our function a little bit. So we start with the outer function being f of x here. So we are replacing the x with g of x. We're going to write g of x instead. So our function f of x is 1 over x, but instead of x, we just write g of x. So our function f of g of x is 1 divided by g of x. And then we know what g of x is. It's 10x minus 12. So we're going to replace g of x with its actual formula, 10x minus 12, and we get 1 divided by 10x minus 12. And that is our function f of g of x. So for finding the composition function, this would be our answer. The next part is that we want to find the domain. And like we did earlier, we worked on those domain problems. We said that having a function divided by, or a fraction where we have x in the denominator, is one of the things that messes up domain. And we say that our denominator cannot equal 0. So we're going to do the same thing here. We're saying that 10x minus 12 cannot be 0 for our domain. So we want to solve for x. In our statement here, we're going to go ahead, we're going to add 12 to both sides. So now we have that 10x does not equal 12. We'll divide each side by 10. And we get that x does not equal 12 over 10. We can simplify this statement. 12 and 10 are both divisible by 2. So we can simplify this to x does not equal 6 over 5. So we now know what x is not equal to, but x can be equal to any other number. And once again, if you want to put this in decimal format, that's all right as well for the exam. But we want to find the domain. We can help ourselves by drawing out a number line going from negative infinity to infinity. And our number here in the middle is 6 over 5. And we're saying that x cannot be 6 over 5, so we're going to have a big circle there. We have a circular point. And our function exists anywhere else. So our intervals, once again, reading from left to right, we're going to have an interval here and an interval here. So going from left to right, once again, starting at negative infinity, we'll go up to 6 over 5. And since we didn't include 6 over 5, we have an open circle. We're going to put parentheses around the 6 over 5 as well. Then the other side of our interval there will start at 6 over 5. And it goes to infinity. And once again, we have parentheses because our point 6 over 5 is not included, and our infinities always have parentheses on them. So we have our two intervals here. Now, the last thing we need to do to connect these is to put in our union. And once we have that, this is our domain. So our domain of f of g of x would be negative infinity to 6 over 5, union 6 over 5 to infinity. So that's how we would go ahead and do part A. Now for part B, we have g of x. So we're using this kind of double composition here. So if we have g of x, we know this is the same thing as writing it like this. So we're going to take our outer function. So we're going to erase the lines that we drew before. We're going to take our outer function, which in our case is g. So we know that g of x is equal to 10x minus 12. So instead of writing x in the original g of x, we're going to write g of x instead. So our original g of x was 10x minus 12, but we're replacing x with g of x. So we're going to write 10 times g of x minus 12. Then once again, we know that g of x is 10x minus 12. So we're going to replace this g of x with 10x minus 12. So we'll end up with 10 times 10x minus 12, and that minus 12 is still sitting there on the outside. So now that we've correctly composed this, we want to simplify. So we can distribute our 10 into our function here. 10 times 10x would be 100x. 10 times 12 would be 112 minus 12. So we have 100x minus 120 minus 12. We have minus 120 minus 12. That's like saying plus negative 120 plus negative 12. And when we add two negatives together, they become more negative. So this will give us 100x minus 132. So this is our composition function. G of x is 100x minus 132. Then we want to find its domain. We want to find this domain of this function. And what we said before, and the problems that we worked on earlier with domain, is that domain is almost always going to start at negative infinity to infinity. And having things like fractions with x in the denominator or having square roots would change that domain. Domain is inherently always negative infinity to infinity unless something changes it. So before in part A, we saw that, our denominator couldn't equal 0, so the x value of 6/5 wasn't included in the domain from negative infinity to infinity. And from part 1, or question 1, we had that square root. We said that whatever was underneath the square root had to be greater than or equal to 0. So we had that inequality, and we solved for that inequality to find domain. The key here is that we don't have either of those things. With 100x minus 132, we don't have a fraction. There's no denominator, so there's no x in a denominator, and there's no square root. So if we don't have either of those things, our domain is just negative infinity to infinity. X can exist everywhere in the function 100x minus 132. There's no x value that would make your function not exist. So our domain would be negative infinity to infinity for a function for part B. All right, so that wrapped up example 6. Let's go ahead and do our last example, example 7. All right, so our last example, example 7, we want to find the inverse function of f of x. We're given our function f of x, it's equal to 5x minus 2 divided by x plus 9. So let's go ahead and go to our notes so we can work on this problem. All right, so we have our function f of x is equal to 5x minus 2 divided by x plus 9. And we want to take the steps needed to find the inverse function of f of x. So in step 1, we say that we want to replace f of x with y. We're just going to write y instead of f of x. So we get y is equal to 5x minus 2 divided by x plus 9. So here's our function. We replaced f of x with y. Fairly straightforward. And step 2, we want to solve for x. Because of our function and how it looks, we have x in 2 separate places. So it's going to make it a little more challenging, but we can still solve for x. The first thing that we want to do to try to solve for x here is that we don't want a fraction. We want to get rid of the x plus 9 on the denominator. So we're going to go ahead and we're going to multiply x plus 9 to both sides to get rid of the fraction on one side and then multiply it on the other. So we had y was equal to 5x minus 2 divided by x plus 9. And we're going to multiply each side by x plus 9. So when we simplify this, we'll get x plus 9 times y is equal to 5x minus 2. So no fractions anymore. This is what we wanted. So we're good from right here. Now we just want to keep simplifying. We're going to distribute this x plus 9 times y. So we're distributing the y inside our function here. And this will leave us with x times y plus 9y is equal to 5x minus 2. All right. Looks good. There's no more parentheses. We've distributed everything. And now that we've distributed everything, remember we're solving for x. So we want all of our x terms on one side, meaning anything that has an x, we're going to bring it to the left-hand side. It doesn't matter if it also has y. As long as it has an x, it needs to go to the left-hand side. And anything that doesn't have an x needs to go to the right-hand side. So we need to have x terms equals non-x terms. So we can go ahead and do that. So we have 9y on the left-hand side. We want it on the right-hand side. So we're going to subtract 9y from both sides. We also have 5x on the right-hand side, and we want it on the left-hand side. So we're going to also subtract 5x from both sides. We see that these 9y's cancel and these 5x's cancel. This leaves us with xy minus 5x is equal to negative 2 minus 9y. So what happened here is that we ended up with x terms set equal to non-x terms. This is what's telling us that we're doing it right. If we have x terms equals non-x terms. I'm going to carry this step up here. Because now what we get to do is on the left-hand side, we can factor out an x. See that there's an x in both terms. So we're going to reverse distribute that x out. This would be x times y minus 5 is equal to negative 2 minus 9y. Since we now have the x by itself and it's just multiplying y minus 5, we want to get rid of that y minus 5. We want x by itself on the left-hand side. The only way to do that now is to divide each side by y minus 5. We don't really care how ugly the right-hand side gets, as long as x is by itself. So we now have that x is equal to negative 2 minus 9y divided by y minus 5. So we did all the heavy lifting. We did the hard part of finding an inverse function of something that looks like a rational function here. Step 3 is 2 last parts. First is we are going to replace all the y's with x's and replace the x with a y. So this turns into y equals negative 2 minus 9x divided by x minus 5. So we switch in our x and our y. Then the very last step is that you replace y with f inverse of x. And we now have that f inverse of x is equal to negative 2 minus 9x divided by x minus 5. And that is our inverse function for f of x. Now your final answer can look slightly different from this in a few different ways. It doesn't necessarily have to look exactly like this. You could redistribute some negatives. You could take some negatives out. It could look a little different, but the main portion here is that this will be the final answer. Even if you take out some negatives, redistribute some negatives, it should still look very similar to the answer that we have here. But any way that you change it by changing around those negative signs or anything would still technically be correct. So there are multiple correct types of answers for inverse function problems. They should all look relatively the same. So, all right, that finished up example 7. Those are all of our examples for our review. So that finishes up our exam 1 review. So if you have any questions about the review, please feel free to email me. If not, Good luck on exam 1. Have a great weekend, everyone, and good luck studying.